All right, so welcome back, everybody. This is going to be our last lecture before spring break. As a reminder, next week we have off. That's going to be spring break. When we come back, we're going to start a new chapter on DC circuits, which is pretty closely related to what we're talking about now. But basically, it's just more sophisticated tools to analyze what's going on in a circuit than we've seen so far. So that's what's coming after the break. That means we're going to finish this lecture on current and electrical resistance today. And this shouldn't take too much more time. We probably will have some time to get to some practice problems at the end. So if you recall, the last thing that we went over was electrical power. And can you just remind me, most general, broad definition of power in physics? What is the definition of power in physics terms?
Amount of work being done over a period of time.
Okay, so we can, in one sense, we can think of it as work performed per unit time. But that's an example of mechanical power. So more generally, it's just an energy being converted per unit time. That's probably the more general way to think about it, okay? And now we're going to talk about power in the context of an electrical circuit. So in particular, this is what I want us to start by thinking about. We have some kind of device. This can quite literally be anything. It can be a heater, it can be a motor, it can be a light bulb, anything where there's current running through the device, okay? This can be whatever you want. What I'm going to show you to start off is that the power of this device, and remember what power means, it's the energy it's consuming per unit time, is equal to I times V, where I is the total amount of current flowing through it, and V is the potential difference across the device. So if you take the current running through a device multiplied by the potential difference across the device, whatever this happens to be, that's going to give you the power, okay? So we'll start by deriving that equation. Then I'm going to show you what happens if we have a specific case of a resistor. Okay, so if that device happens to be a resistor, then we'll derive these two equations, okay? So let's do the derivations on pen and paper, and then go back to this to discuss it. Okay, so here we go. The power output of our device. We want to think of it in these terms. It's the amount of energy consumed, and I'm going to just call that delta U for our purposes, divided by the time it takes to do that, which I'm going to call delta T. And again, the picture is you have your device. I'm just going to draw it as some black box. And points A and B are at either end of the device. And again, the idea is we have current I running through it, like this. Okay, so can anyone remind me, this goes back to the chapter on electric potential. But let's say I have some amount of charge that's moving across a potential difference. Okay, how do I write the energy, or the change in energy that that charge undergoes when it moves across the potential difference? Do you remember? This is given by Q delta V. Remember this, right? Q times delta V, if we take the amount of charge that's moved across times the potential difference, that's going to give us the change in energy of that charge. So I'm going to write this in a slightly different way, okay? Because charge is just continuously flowing across this device if there's current through it, I'm going to call the amount of charge delta Q, just to indicate it's a small piece of some larger amount of charge. And the potential difference, using our current notation, we just use V for that, okay? In the context of electrical circuits, when we're talking about a potential difference, we usually drop the delta. We just call it a V, okay? But that's the idea behind this. So therefore, the power should be delta U, which we just established is delta Q times V divided by delta T. So we have the time on the bottom there. And I'm just going to write this in a slightly different way. We have delta Q over delta T times V. What's delta Q over delta T? That's the definition of something. Current is defined as charge per unit time, right? Charge per unit time flowing through our device is delta Q over delta T. That's the electrical current I that we initially had pointed out on the diagram. So this is where P equals I times V comes from. Okay, and it's a very general statement. If you have some device with a potential difference across it and some current flowing through it, that's the power. Okay? Now, let's start with that. So we have P equals I times V, which is a pretty general statement we can make. And then let's see specifically what happens when we think of our device as being a resistor. Remember, an ideal resistor follows Ohm's law, which says that V equals IR. The voltage across a resistor equals the current running through it, I, times its resistance, R. So if that's the case, we can plug that into our formula for power, and we'll get I times V, but for V, I'm going to replace that with I times R, which will give me I squared times R. So that's where that formula comes from. The power consumed by a resistor is given by the current squared times the resistance. Okay? There's another way we can write this. You see, I can either swap out the V term, which is what I did here, or I can swap out the I term. So let's write this another way. Let's write I equals V divided by R in Ohm's law. And let's replace I in our formula for the power with V divided by R. So now what we have is P equals V divided by R times V, when I make the substitution for I right here, which is simply V squared divided by R, okay? So let me just put a check mark by the three formulas we have. We have this general expression for power, which is I times V, and then we can express that as either I squared times R or V squared divided by R if we're dealing with an ideal resistor that follows Ohm's law, okay? Any questions on that? So these are going to be very useful formulas in the next two chapters. Okay, so that's where all this came from. All right, we have the general expression for power, and it can be written as I times V. It can be written as I squared times R, or V squared divided by R when it comes to a resistor. So a little bit more on that. Remember, power is referring to energy being transformed from one type to another. And in the case of a resistor, what's happening is you're taking the kinetic energy of these moving electrons that are flowing through the resistor, and that's being transformed into heat, essentially. In other words, because these moving electrons, they don't flow unimpeded. They're going to crash into other electrons and atoms within the material. When those collisions happen, it heats up the material. Okay, it causes the thermal energy, the vibrational energy of these atoms to increase. And we quite literally feel that as heat. So a very simple electrical heater is nothing more than current flowing through a resistor, generating a lot of thermal energy. Okay? So do we have any questions on that? All right, let's do an example. So here's what we have in this example. A light bulb is designed to have a power output of 55 watts when it's connected to a 120 volt source. So the first question is, what is the resistance of this light bulb? Okay, now, let's suppose that we connect the bulb to a 12 volt battery instead of an 120 volt source as we're supposed to. What current flows in the circuit in that case? And what is the power output of the bulb in that case? What we're going to find is if you use a smaller voltage that you apply to the bulb, you're going to get a lot less power output, as you might expect. Okay, so it's not really going to function properly. A few assumptions we're going to make here. One, we're going to assume that the resistance of the bulb doesn't actually change. We know from the previous lecture that if the bulb heats up or cools off, the resistance could change. We're just going to ignore that effect for this problem, for simplicity. And also, we're gonna ignore any resistance in the wires that connect the bulb to the battery, okay? So let's get into this one. So to answer the first question, what is the resistance of this bulb? I'm just gonna write down the statement. P is equal to 55 watts when V is equal to 120 volts, okay? That's what we're given. So I want to use this to find the resistance. I have many different formulas for power. I have these 3 different ones, but the one that's probably going to be the most useful here is P equals V squared divided by R, right? Because I can directly solve for resistance as V squared divided by P. Make sense? Okay. My voltage V is 120 volts, square that. And my power is 55 watts. Now, can someone do that calculation for me?
261.8.
Yeah, so this is 261.8. Technically, we'd want to keep just 2 sig figs here. And what units do we expect this to come out in, by the way? It's a resistance, so ohms, yep. But we want to round that to 260 ohms with 2 sig figs. Okay, let's do the units real quick. It's probably not immediately obvious that volts squared divided by watts gives you ohms. So let's show that that's the case. So in this calculation, again, I have units of volts squared divided by watts. All right. Here's what I'm going to do just to show how the units work out. You can really go down a long rabbit hole getting lost in the units, so I'm just going to show you probably the most direct route to go. Since I have volts squared, I'm going to take one of those factors and just leave it as is. But for the other one, I'm going to write it in the following way. A volt is a joule per coulomb. Remember that? Okay, what is a watt equivalent to? A joule per second. Remember that? So hopefully you can see, just by looking at this then, that the units of joules cancel, right? And I can take this C and put it on the bottom. And now we have coulombs per second on the bottom and volts on top. Now, what is a coulomb per second equivalent to? That's an amp, right? That's a unit of electric current. So what we have here is a volt per amp, isn't it? And hopefully you recall that that's what an ohm is. Okay? So that's how the units shake out here. Okay? All right, now let's do the next part. So now we'll suppose that we're not connecting our light bulb to 120 volts, but instead to a 12 volt source. So there are 2 questions we wanted to answer. I, what is the current? And P, what is the power? So let's answer both of those questions. Okay. How should I go about getting the current? Probably the easiest way is just to use Ohm's law, V equals I times R, right? Because I know the voltage applied to my bulb, I know the resistance of my bulb, so that immediately determines what the current is, right? So the current should be V divided by R. But now we're supposing the voltage is only 12 volts. But the resistance, again, we're assuming that's not changed. 261.8. And what's, again, the equivalent unit for an ohm? Volt per amp. So we can see this comes out in amps, right? All right, can someone tell me how many amps of current we're dealing with here?
0.46 amps. 0.46.
Yeah, 0.46 amps, that's right. That's rounded to the 2 sig figs. I'm going to write it down with 1 extra digit just for our next calculation. This is 0.0458 amps rounding to this answer, okay? All right, cool. So what could I do then to get the power output?
I squared over R.
Yeah, I could literally use any of the formulas we derived. I could use I times V, I could use I squared times R, I could use V squared over R. You can verify whichever one you use here, you'll get the same result. I don't know, which one do you want to use? First one, second one, third one?
Okay.
All right, second one it is, let's do it. So I squared is 0.0458. Amps squared resistance is 261.8 ohms. And this gives us the power. What is that power?
0.549.
So I'm just going to round that to 0.55 when we keep two sig figs, watts. So that's 100 times less power for using 10 times less voltage. Because power right here, as you see, depends on V squared. So that should make sense, right? Any questions on that? Okay. Let's do this one. This one I want you to try to work out at your desk, and then we'll go through it together. So consider these two different circuits that I'm showing you. Circuit number one consists of a battery whose terminal voltage is V, connected to two bulbs, which both have the same exact resistance, which I'm just going to call R. Circuit number two, it's the same deal, except now I have 4 bulbs, but again, they're all identical. They have the same resistance, R. My question for you is, if we consider the total power output of all of the bulbs in each circuit, so in the first circuit, the total power output of the 2 bulbs, in the second circuit, the power output of these 4 bulbs, which one is greater for the total power output? So try to work it out symbolically, what the total power output for each case is, and then just tell me which one's greater, okay? That's what we'll do. In other words, your expression for the total power output should just be something that only involves V, the battery voltage, and R, the resistance of each bulb. Just based on that, you'll be able to see which one's bigger. See what you got. So you essentially just combine the resistances. Yeah, you can do that. Technically, we don't know that trick yet. But yeah. That's good. You're looking at it. All right, so let's put this one to a vote. All right? And you have to vote. Mandatory voting. Who thinks it's A, that the total power output of the bulbs in circuit number 1 is greater? B? C? Okay. Only a few for B and C. It is A. Okay, that is correct. So here's kind of the conceptual idea. Because the total resistance of the bulbs in circuit number 2 is greater, it's going to draw less current to these bulbs. Okay? And since the power depends on the current squared, that's going to be a larger effect than the fact that we have more bulbs. Okay? But let's actually work this out mathematically. Okay? Let's go into some detail here. So first I'm going to analyze the circuit that has 2 bulbs, and we can take what we find from this circuit and directly apply it to the one with 4 bulbs. Okay? And some of you I saw did a little trick where you combined the resistances. You can totally do that, but I'm just going to show you a different way to do it. So here we go. This is the one with 2 bulbs. So in my diagram, I'm going to show 2 resistors, R and R, connected to a battery. We remember how this works with the current flow. The negative terminal is down here, the positive terminal is up here, and our conventional current is the direction that positive charge would flow. So positive charge would move off the positive terminal and want to come back around to the negative terminal, right? So that's how we know I is going this way. Now I'm going to label 2 points on our circuit. Let's call this point B up here. Let's call this point A down here. So the potential difference between points A and B, this means I'm starting at point A and I'm going to point B. This can be found 2 different ways. I can either go across the battery to get from A to B, or I can go across both of these resistors to get from A to B, right? And either way I go, I should get the same result because I'm talking about the same 2 endpoints. Okay? Okay. So the voltage across the battery, what's that? Well, that's just V. And it's positive going this way because I'm going from the negative to the positive terminal of the battery. Remember, that's the way this works. If I were going the other way, it would be negative V, but that's how it works out when we're going this way. For the resistors, the voltage across a resistor is given by I times R, right? But we have to be a bit careful in a situation like this. Remember the rule that we determined last time? If I'm going with the current, then there's a negative potential difference, so we lose voltage. But if I'm going against the current, there's a positive voltage, okay? So in this case, going from A to B, we're going against the current. So I'll have positive I times R going across the first resistor, and then positive I times R going across the second one. So V is equal to just 2IR. Something you could have probably figured out with going into all this detail, but I think it's worth seeing in detail, okay? So the current is what? It's going to be V divided by 2R, right? Okay. So then, what's the total power output of the bulbs? I'm going to have 2 different bulbs, so each one is going to be given by I squared times R, but I'm going to multiply by a factor of 2 because I have 2 bulbs, okay? And then what I'm going to do is plug in V over 2R in place of our current. Cool? All right, so I have V squared divided by R. And what numerical factor do I have in front? Just a half, right? Because I have 2 on top, 2 squared on the bottom, so it's just 1/2. Okay, so we're not going to go through all this same level of detail with 4 bulbs. Hopefully you can see that in the case of 4 bulbs, our current would be V divided by, instead of 2R, what would it be? Yeah, it'd be 4 times R. If you repeated the same process with 4 bulbs, that would lead to you having a factor of 4 on the bottom here for your current, okay? And then for the total power output, well, each bulb has a power output of I squared times R. but we have 4 of them now. So there's now a factor of 4 out there as well, okay? So we have 4 times I, which is V over 4R squared times R. So this is V squared divided by R. What numerical factor is out front? It's not 1. 1/4. Okay, so more bulbs in this sort of configuration actually gives you less power output. Okay? So again, the reason for that is with more bulbs, you get less current. And sure, you have more of these terms to add together for your power, but the current is squared. So that's a bigger effect than simply having more bulbs. Okay? Any questions on that?
What was the question asked?
It was asking if we, all right, so go back to the slide. If we compare these 2 circuits,
Yeah, they was asking for the greatest power.
yeah, and it's circuit number 1, the one with 2 bulbs, not the one with 4 bulbs.
Let's say just practically, because we have 4 light bulbs, and you know the power is the energy consumed. If you have 4 light bulbs, the same resistance.
Yeah, so these ones are consuming energy at a faster rate than these ones in total.
Yeah, because when we have the relationship 2I squared R and 4I squared R, can we conclude? Or have to go further to conclude?
I'm sorry, I didn't catch the last part.
When we have the relationship for the 2 circuits, the first one was giving 2I squared R.
Yeah.
The second one was giving 4I squared R.
But there was different currents in each case. In this case, there was less current, so that's why. Yeah, because effectively there's more total resistance in the circuit, so you're going to draw a lot less current. That's why it worked out this way. Okay. Okay, so just want to make a few quick notes about this formula in particular. For a resistor, we found that P equals I squared times R. And more generally, it's not necessarily just for resistors. A resistor is typically referring to something you deliberately put in a circuit to control the current in some way. But everything in a circuit at some level has resistance. Like even the connecting wires and the cables in a circuit have some resistance. So, yeah, what's up?
So the more bulbs, the more so the more resistive, like the more resistors, the more battery power is used faster than
Yeah.
resistors, pretty much.
No, it's exactly the opposite. The fewer resistors we have, that's circuit number 1, the faster we're consuming the electrical energy from the battery. Okay. So, yeah, resistive losses. Let's start there. Anytime you have electrical current running through wires or through cables, you're always going to be losing some energy. Remember, P equals I squared R is referring to a type of power, type of energy being transformed from electrical energy to thermal energy. And when you're just transferring electrical power through a cable, that's not desirable, right? So for example, if I'm transferring power over a high voltage line from a power station to a neighborhood, I don't want these resistive losses, okay? That's just power wasted as far as we're concerned, all right? So that's something you always have to consider, is that there will be resistive losses present, and sometimes you want to minimize those resistive losses, especially if you're just trying to transfer power through a cable, okay? The other thing to consider here is the idea that you can overload a circuit, okay? So here, I want you to consider the way a household is typically wired with circuit breakers, and on a smaller scale, devices can have fuses in them. All of that is just to prevent overloading of a circuit. So here's the idea. When current runs through a wire, it will tend to heat up. Okay, because we're transforming this electrical energy into thermal energy, we're going to heat up a wire. The more current runs through it, the faster we're going to heat it up. Okay? And at some level, you can have a dangerous amount of current running through a wire where it's heating up so much that it could damage your circuit or even start a fire. okay? So we don't want that to happen, which is why we have these safety devices like fuses and circuit breakers, which will just stop current from flowing if it gets too high. So they're designed to detect when current gets to an unacceptably high level and just shut the circuit off in that sort of situation.
Yeah, I would have thought of like a real world example of this. My dad works on some satellites that like when they're launched, they have liquid helium reservoirs in them because like they're space telescopes. And does the act of running the telescope itself, just the very little energy there, can interfere with the observations if it's not, it's like super cool to almost 0 Kelvin.
There's another reason for that too, though. In a telescope, so this is a little bit off topic, but just a quick comment on that. Anything that has a non-zero temperature is giving off light. So a human body, if you look at it with infrared goggles, you'll see it's giving off infrared radiation. Every single object is giving off some radiation as long as it's not at absolute zero. So if you have a telescope, that light can contaminate your images that you're trying to take of distant objects like stars and galaxies.
Yeah.
That's one of the main reasons you cool off the electronics in a telescope, is just to get rid of that like thermal light that's contaminating everything. Yeah.
And you can also technically say that just every object is getting off light because no object in the universe is at absolute zero.
Yeah.
It's not possible at this point.
Yeah, exactly. So, and again, this is just a little off topic, but if you've ever seen like a really hot piece of iron, it will glow red, and then if it gets even hotter, it glows yellow. Every single object does that. It's just, for very cool objects, you don't detect that light. Our eyes are not sensitive to infrared light, but that's always present. And yeah, in a telescope, that sort of light can contaminate the light that's coming from stars and galaxies that you're trying to take images of.
Yeah.
That's one reason for, pretty much every telescope has some kind of cooling mechanism for that reason. Yeah. Okay. Interesting questions. Now let's talk about the last topic in this lecture, which is the microscopic view of electric current. So all we've done so far is come up with some formulas that describe some very simple things like the relationship between voltage and current, and the relationship between voltage, current, and power in an electrical circuit. But we haven't really talked much about what is the origin of these things. For example, what is resistance at the microscopic level? What's happening to individual moving electrons that causes electrical resistance, okay? And what does current look like when we look at it on a microscopic level? That's what we want to get at here today. Okay, so we'll start off just kind of qualitative, okay? This is a microscopic picture of current flowing through a wire, okay? So here's what we have. In blue, I'm showing you the individual atoms of whatever metallic material is making up this wire. So maybe copper atoms in a typical wire, right? Then in red, I'm showing you the free electrons. Okay, remember, assuming the wire is metallic, it's going to have some free electrons that can just move throughout the wire. That's what makes it a conductor in the first place. Okay? So, normally, in a circumstance where there's no moving charge, there's no electric current, we would say the E field inside of this conducting material is 0. But that's not the case here. We're imagining that there is electric current, there are moving charges, so the E field inside the wire is not actually 0. There is some non-zero electric field inside of this wire. And you can see that because as you go across the wire, there's going to be some kind of potential difference. Let's say that the direction of that potential difference is like this. We're going from high V to low V here. Maybe just to make up some numbers, we're going from 12 volts to 11 volts as we go from left to right across the wire. So you tell me, what direction is the electric field in this case?
To the right.
It has to be to the right because E fields go from high to low potential. So that's the first thing to know. We must have an E field going this way. All right, so what direction is our current in that case? Conventional current. Also going to the right. The idea behind conventional current, if you remember, is this is the direction that positive charges would be moving. Positive charges just feel a force that's going with the E field, so they'd be pushed in the same direction that our E field is pointing in to the right. So that's our conventional current. Okay, but what about the actual motion of electrons, which are negatively charged? To the left, yeah? So that's the picture. If there's a potential difference across the wire, and again, you can create this kind of potential difference by hooking it up to a battery or something like that, right? You'll have this E field. That E field is responsible for setting the charges in motion. It's the E field that's pushing things around within the wire, okay? But let me ask you this. Let's say we keep track of just one of these electrons and try to see how it's moving through the wire. Is it just going to move unimpeded, or is it going to start to bump into things? Yeah, it's going to have a very perilous journey going through the wire. It's going to constantly crash into atoms and other free electrons. So you don't want to think about this as just it moves in a straight line from right to left, right? Instead, it's going to look something like this. It's going to be this sort of pinball effect, right? Frequent collisions with the atoms and the other free electrons in the wire. But overall, it's moving to the left, okay? But it's doing so in a very indirect way.
For that, would that be a negative potential difference, like going from high to low?
Yeah, in this direction, yeah. Yeah, it would be. Okay. So here's a few things I want to point out about this, okay? The first point is this. The free electrons, we might expect that because there's an electric field, that the free electrons would be accelerating. So they would just keep speeding up and speeding up over time. That's not actually the case. Instead, the free electrons pretty quickly, almost immediately as far as we're concerned, on the scale of, fractions of a second, they're going to reach a constant velocity. And the reason for that is, even though the electric field is accelerating them in one direction, that motion is being impeded by these collisions within the material. Okay? And those two effects balance each other out in a very short amount of time, at which point you reach a constant velocity. It's very, very analogous to the idea of terminal velocity when something falls. We're all familiar with this idea of terminal velocity for a free-falling object. Can anyone explain that to me real quick? How does terminal velocity work?
When the acceleration caused due to gravity is equal to the acceleration in the opposite direction due to air resistance.
Perfect. That's a perfect explanation. Terminal velocity is this. Gravity would tend to accelerate objects straight to the ground. And of course, in a vacuum with no air resistance, a free-falling object would just continuously accelerate, right? But in the real world, we have air resistance. So there's a force of gravity going down, and then there's the air resistance going up, assuming we're falling like this. So if I drop this object, pretty quickly it just assumes a constant velocity because there's a balance of those two forces. That's more or less what's going on here, right? The E field tends to force the electrons to the left, but the collisions exert a force in the opposite direction. In a pretty short amount of time, those effects balance each other out. And instead of just accelerating down the wire, electrons are moving at a constant velocity down the wire. Okay?
For denser metals, do the electrons go slower?
So yeah, what we're going to find as we develop some of our equations is that the density of electrons in the material does matter at some level. We'll get to that. So not only do we have this idea that electrons are going to reach some kind of constant velocity, but this is the origin of resistance. These collisions are the reason the current is limited. You don't just get infinite amounts of current when you hook up a wire to a battery. What's limiting the current is the collisions of your free electrons with atoms and other free electrons in your conductor. And not only that, those collisions are responsible for generating the heat that we talked about before. If an electron collides with an atom, it's going to cause that atom to vibrate a little bit faster than before. That is what thermal energy is at a microscopic level. So that explains almost everything that we've talked about so far. Does that make sense? And I guess the last thing I want us to understand is this. Remember, resistance has a temperature dependence to it, right? We came up with this formula that explains how electrical resistance can increase as temperature increases. And the exact details of that depend on your material. But let's just get an understanding of why it is that when temperature goes up, so does electrical resistance. Okay? So here's another animation for you to look at. So in each of these animations, we are shown free electrons moving through a wire. In the first case, we're going to imagine the wire is cool, so it's at a lower temperature. In the second case, we're going to imagine we have a hotter wire at a higher temperature. So what does it mean to be at a higher temperature? Temperature is just a reflection of the microscopic random motions of the atoms and molecules that make up some material. So if we're talking about solid material, the faster the atoms are jiggling around in their lattice, the higher the temperature is, okay? But for a hotter wire with atoms that are jiggling around faster, that presents an opportunity for even more collisions than in a cooler wire, okay? The collisions are going to become more frequent in this hotter wire. And that's why the resistance goes up when the temperature goes up. Again, the details depend on exactly what material you're talking about, but that's generally going to be true in metal wires, okay? As the temperature goes up, so does your resistance, because we have more frequent collisions. Okay? Yep?
I was gonna say, with solid objects with their matrices the way they are, the vibrations will be that large then, that it would cause that level of heating?
Yeah, and again, the size of this effect depends on your material, but that's generally going to be true.
Okay.
Okay, so that was all pretty qualitative so far. Now let's get into some equations that describe what's going on at a microscopic level when you have electric current. Okay, let's start with some definitions. Okay, I want to define three things for you right here. The first one is something called current density. This is an important concept. We're going to actually see this in later chapters, particularly when we get to magnetism. So what's current density? Current density is given by lowercase j, and it's defined in this way. It's current per unit area. Okay, pretty simple statement. Current on top, I, area on the bottom, A. But what does that actually mean? This picture should help us. So let's say we're dealing with free electrons moving through a wire, just as our typical example, right? So if we take a cross-section of the wire, and most wires have a cylindrical shape, so this cross-section A is going to have a circular shape to it. We could ask the question, how many charges are moving through that area every second, right? What is the total amount of charge moving through that area every second? That would be what's called our current, okay? But if we were to divide by that area, that would give us the current density, okay? So charge per unit time, that's current, charge per unit time, then dividing out the area is your current density. So if the charges are moving through a smaller area, you have a thinner wire, you have a larger current density, right? If you have a bigger area that the charges are moving through, you have a smaller current density. Does that make sense? Okay. So that's the meaning of J equals I divided by A. All right, another thing that's going to come into play in some of the equations that we'll derive is the idea of number density. Number density is given by lowercase n. It's a number density, well here, let's back it up. When I refer to density in general, right, it's something per unit volume, right? It could be mass per unit volume, charge per unit volume, that's charge density, right? Number density is just number per unit volume. Number of what? Number of free charges. Okay, free electrons typically that are carrying the current. Okay, so number density is the number of moving charges per unit volume. Here's how we define that. Lowercase n is for number density. That's going to be capital N. That's the number of moving charges that are present in your material. And again, we're talking about a conductor. We're talking about the free electrons. Divided by V, which is the volume. Okay? So in other words, large number density means there are a whole lot of moving charges per given volume. A smaller number density, the charges are pretty sparsely spread out. Okay? Lastly, drift velocity. So we had discussed that, the velocity of your charges moving down the wire is more or less constant. Okay? In other words, the charges are not speeding up because there's sort of a balance of two effects, which is the electric field pushing it through the wire and the collisions it's experiencing that impede its motion. Okay? So when we refer to the drift velocity, we're talking about the average velocity of the moving charges that carry this current. So in reality, there's some randomness involved in this, but if we talk about the average velocity that charges are moving down the wire, that's what we call our drift velocity. VD for drift velocity. Okay? So are we good on these definitions? All right. So then we're going to derive a relationship between all of these different variables that I just defined for you, which is the current density, the drift velocity, and the number density of charges. So here's how this is going to go. Well, actually, let's start just by looking at this picture. Again, if you want to imagine something specific here, imagine a cylindrical wire with electrons moving through it like this. Okay? Let's say the electrons are moving to the right. And in particular, we're going to focus on what happens when these electrons move through this surface right here. So I've drawn an imaginary little surface with area A, and we're going to focus on what happens when the charges move through that particular surface. Okay? So let's start with this. Let's try to figure out how to write down a formula for the total charge that's moving through this area in a time interval delta t. Okay, so delta t can be whatever you want. Let's say it's 1 second. That would be asking how much charge is passing through that area every 1 second. Let's just come up with a general formula for that.
That's not just current, that's not just the definition of current.
Yeah, it's pretty much that, but we want to write it in terms of these variables we've developed. Yeah. So I want to think of it this way for the time being, okay? Because we're talking about a total charge. That would be given by this. Each particle has a small amount of charge. So if I take the charge on each of those particles, and then I multiply by the number of particles that have actually passed through here, well, that will give me the total charge that has passed through this area. Does that make sense? So just take the number of charges we have times the charge on each of those particles, and we'll get the total charge. So let's put that symbolically. The total charge that passes through in time delta t, I'm going to call that delta Q. Okay? And N, capital N, that's the number of particles. And then lowercase q, that's the charge per particle. So if we were talking about electrons, we would know to put the elementary charge there, right? But I want to be a little bit more general. This is just the charge on each particle. All right? Okay, the next thing I want to go over is this. The number of particles that are present is equal to this. It's our number density times the volume. That should make sense, right? Because number density is just number of particles divided by volume. So if we multiply that by volume, we just get the number of particles. Okay? In other words, capital N number of particles is equal to lowercase n, number density times v, which is our volume. Now let's be really clear about how this is going to work, okay? Since we're talking about some time interval delta t, a whole bunch of particles are going to move through in that time interval, right? So if a particle moves through the area at the very start of that time interval, at the end of that time interval, now it's going to be over here somewhere. It's going to have moved past that surface. In other words, it's going to have covered some distance this way, okay? So if I want to think about the volume, okay, that's relevant in this formula, that would simply be this volume right here. It'd be the area times the distance covered by those particles. And that would give me the volume. That would then give me the number of particles that have passed through. Does that make sense? So let's think of it this way. For the volume, let's think of that as the area times the length, or times the distance traveled in our time interval delta t. Okay. For the distance traveled, that's just the speed at which the particles are traveling through the wire, which is lowercase vd, that's our drift velocity, times delta t. If we take this speed times the time, that will give us this distance covered. And again, what I'm saying is we take this distance covered times a, that gives us the volume of particles contained right here. So what I'm going to do is make that substitution for L. So the number of particles is now lowercase n times the area times the drift velocity times delta t. Okay? That's our formula. Are we good on that? So here's what I'm going to do with that. This is going to tell us the number of particles that have traveled through this area in time interval delta t. If I plug that in here, that's going to give me the charge that's passed through in time interval delta t. And then, David, I'm going to do what you said and apply the definition of current to finish this off, okay? So here's what's next. Just a simple substitution of the capital N formula in our delta Q formula. So we have delta Q is capital N times lowercase q. So basically this whole expression here times lowercase q. Remember, lowercase q is the charge that each one of these particles has. So we have delta Q is lowercase q, lowercase n, a, vd, delta t. It's kind of a lot going on there, but remember what all these things mean. Okay, here's what we'll do next. This is what you asked about. We're now going to apply the definition of current. The definition of current is delta Q divided by delta T. It's the amount of charge that has passed through this area divided by the time interval it took to pass through that area. That's what current is referring to. So what do we get when we divide out the delta T from here? We just cancel it out, right? It's pretty simple. We just get Q, N, A, V, D. When we divide out the delta T, we just get rid of it at the end of the expression, okay? But we can take one further step. What's the definition of current density? This is current. How does current density work?
Current over a given area.
Yeah, we would take this current and we would divide by the area that the current is traveling through. And that would give us current density. So J for current density is I divided by A. What happens when we take this expression for I, we divide out the A term? Just cancels it out, right? So that gives us something kind of simple, actually, which is Q and VD. That's the big result here. The big result is current density is Q lowercase n VD. Current density equals the charge of each particle, number density of particles, drift velocity of particles, all multiplied together. Okay? Make sense? All right then. So we are going to make a calculation using this result, and it's going to be probably kind of surprising, okay? So here's the situation. We have a cylindrical copper wire with a 3.2 millimeter diameter. So that's a pretty typical diameter for a wire in certain circuits you may find in the real world. Let's say it's carrying 5 amps of current. Okay, it's a pretty decent amount, but not unreasonable. Let's find the following. The current density J, the number density of free electrons, that's lowercase n, and then the drift velocity of the electrons. Here's some information we're going to need to know, okay? So I'm just going to give it to you on the slide, and then I'll show you how we actually apply it. Copper, we're assuming that this is a copper wire, right? So the density of copper is 8.96 grams per cubic centimeter. So that's the mass per unit volume of copper. Copper also has a molar mass, and if you don't know what this means, I'll explain in a second, of 63.5 grams per mole. Okay, mole, what is that all about? That is just a number of atoms, okay? A mole is kind of like saying a dozen, right? It's just a way of talking about a large number of things. A mole turns out to be 6.022 10 to the 23 atoms. If you've taken chemistry, you're familiar with this. But if not, just think of it as a way of counting up things, okay? All right, so that's what we have. Last piece of information, we're going to assume that there's just one free electron per copper atom. In a metal, that's typically a reasonable assumption, that there's just one free electron per atom, okay? So let me ask you this, okay, drift velocity. We have this wire, it's carrying 5 amps of current. What do you expect the drift velocity to be, like in meters per second? Thousands of meters per second, a couple meters per second?
I would say what we've been seeing before, like magnitudes of like 10 to the 5.
All right, so we're expecting pretty large speeds, right? Is anyone expecting something completely different?
Like 2/3 the speed of light.
2/3 the speed of light? You'll be surprised, it's actually tiny. It's like crawling speeds, okay? That's sometimes a surprising result, but I'm going to show you that's how it works out, and then we'll try to make sense of it, okay? It's like a couple millimeters per second or something like that, I think. It's really slow. So here, let's go through this. Let's start with the current density. Now for this, we can pretty much do a direct calculation because J, the current density, is the current divided by the cross-sectional area of our wire. And pretty much, anytime we're dealing with a wire, you can assume a cylindrical geometry. It's going to have a cross-sectional area that is circular, so that's pi r squared. Okay? What was our current here, just to remind me? That was our 5 amps of current. Okay, and then the radius, well, we were not directly given the radius, but remember, radius is half of the diameter. So if the diameter is 3.2 millimeters, we're just going to take half of that for the radius. And a millimeter, by the way, is 10 to the minus 3 meters. That's our radius. In meters, we're squaring it. So what we'll get is a current density measured in amps per square meter. That would be our SI unit of current density. Can someone tell me what that works out to?
I got 6.22 times 10 to the 5 amps per meter squared.
Yeah, and that should make sense that we get such a large number because a meter squared is a gigantic area compared to the cross-section of this tiny little wire, okay? So 5 amps are running just through that tiny little cross-section. Imagine how many amps would be running through it if we had the same current density but spread out over a meter squared, right? So that's why this number is so large. Okay, let's do number density of free charges, or free electrons in this case. For this, what I'm going to use is kind of a unit conversion sort of method. Okay, we're given the density in terms of mass per unit volume of copper. So we should be able to turn that into a number density just by doing some unit conversions. Okay, that's what we're going to do now. So here's how it's going to work. We're going to start with this. So we're trying to solve for number density, which is lowercase n. And I want this just to be, let's be clear about what the goal is. This is the number of free electrons per meter cubed. That's ultimately what we want this to come out to. So if we treat it as a unit conversion, where this is the unit we're trying to get to, this should work out just fine, okay? So we'll start with this. We're dealing with copper, and copper has a density, as we're given, of 8.96 grams per 1 cubic centimeter. Okay? So this doesn't have the units I want. For one thing, it has cubic centimeters on the bottom, and it has grams on the top, whereas I'd rather have that be free electrons. Okay? So we'll have to take a few steps. How do I do the first part? How do I convert cubic centimeters to cubic meters?
No, it's 100 over 1, and then you cube that.
Yep, perfect. It's 100 centimeters for every 1 meter. I don't want to just leave it at that because I need to cube the entire conversion factor. So centimeters cubed cancels here, and then meters cubed ends up on the bottom, okay? Let's take the next step. We were given the so-called molar mass of copper. For copper, it's 63.5 grams per mole. For our purposes, we just want to think of that as a conversion factor. 63.5 grams is going to go on the bottom because I want grams to cancel like this. And that's going to have 1 mole on top. So I'm just applying the molar mass right there. Okay? And let's take note of where we've canceled units. We've got grams canceling, centimeters cubed canceling like this. Okay? All right, so we want to do a little bit more. The next step I'm going to take is 1 mole is the same as 6.022 10 to the 23 copper atoms. Okay, that's just the definition of a mole. 6.022 10 to the 23 atoms constitutes 1 mole. Okay? So let's see what we have so far. Now we have the number of copper atoms per cubic meter. That's almost what we want, but what we actually want is the number of free electrons per cubic meter, right? So that conversion factor is actually super easy. There's 1 free electron, as we were told, per 1 copper atom. So that doesn't really change anything, but it's important just to write that. Now we have number of free electrons per cubic meter, which is exactly what we need. Could someone multiply those factors out? We're going to do 8.96 times 100 cubed times Avogadro's number, 6.022 10 to the 23, divided by 63.5. This is going to be a gigantic number. Yeah, you said 8.49?
Yeah, and 7.
10 to the 28, right? Okay, good. I think, yeah, actually, yeah, 497, right? Yeah,
Yeah.
thank you. All right, cool. Here's how we want to think about the units, okay? On top, I wrote down free electrons that's the thing that we're counting, but technically when you just count a number of things, that doesn't have a unit associated with it, right? So really our only units are meters cubed on the bottom. So I can write this as inverse meters cubed, okay? Go ahead.
And that's the number of moving charges over a certain value.
Yeah, so every meter cubed of copper has 8.497 10 to the 28 free electrons in it. That's what this is saying. Okay? And again, each material is going to be a bit different, but for a conductor, you're in this general order of magnitude. Okay? Now let's do drift velocity. This is going to be kind of surprising, like just how small this comes out. So for this, we're going to use the equation we derived. J, our current density, is equal to Q, the amount of charge per particle, times N, our number density of particles, times Vd. So Q is just going to be the charge of an electron, and we'll simply take the absolute value of that because we just want to get a speed out of this, okay? So Vd is equal to J, our current density, divided by Q, times N, our number density. So here's what we have. J is 6.22 10 to the 5 amps per square meter. Let me write it to you in this sort of way. An amp is a coulomb per second, right? And then we have square meters. So I can write that as coulombs, inverse seconds, inverse square meters like this. And then Q, that's going to be, we're talking about electrons here. What is the charge of an electron? What? Yep, 1.602. Again, I'm just getting the speed out, so we don't care about the negative sign right now. The magnitude of the charge is 1.602, 10 to the 19, minus 19 coulombs. Right? Okay. Then our number density is what we found here. So it's 8.497, 10 to the 28, inverse meters cubed. So coulombs go away. One factor of meters remains when we do this, and then we'll end up with meters per second. Can someone crunch those numbers for me?
You said it was a small number. Is that because like the amount of electrons, so there's so many collisions happening, it's reducing?
Yeah, that's right. But let's just get the number first, then we'll discuss why it's so small.
4.563 times 10 to the -5.
Yeah. 4.6 times 10 to the -5 meters per second. That's tiny, okay? That's like a, I don't know, microscopic dust mite or something crawling across the table type speed. So yeah, let's discuss why this came out so small and why it makes sense, okay? So yeah, there are a couple ways you can get a large current, right? You can either just have a whole lot of charges moving very slowly, or if you have very few charges, they have to move very fast to give you a large current, right? In the case of a conductor, there are just so many charges, you can have tiny speeds and still get a decent amount of current as a result. But yes, what's slowing these particles down is all those collisions. So let me ask you this then. Okay, I'll turn on the light, and I don't know, there might be like 20 feet of wire, between the power source and the light. So does it just take hours for the light to turn on? No. Can anyone reconcile that idea?
There's free electrons at the tip of the wire waiting.
Yeah. What were you going to say?
No, I was gonna say maybe if you have a voltage high enough, push it through faster or something like that right now.
Well, it's simpler than that, right? See, there are free electrons throughout the entire wire. What's pushing the free electrons around, causing the current in the first place? It's the electric field that's in the wire. The electric field appears almost instantaneously. Like that is at the speed of light, how quickly the electric field changes, okay? The charges that are being pushed around by that electric field move very slow, but the electric field gets set up almost instantaneously. So that's why you don't have to wait, many hours for the lights to turn on, okay? Make sense? Okay. So now let's try to do this. We've been saying this whole time that if there's current flowing in a wire, there must be some electric field in that wire pushing the charges around to cause the current in the first place. So let's try to come up with some way of calculating what the electric field actually is. Let's see if we can characterize it, okay? So here's the picture you should have in mind. We have some kind of segment of wire. Just imagine it's like a cylindrical segment of wire with some current flowing through it. Let's label the length of this segment of wire L, and let's label the area, the cross-sectional area of this wire A. Okay? So I'm in particular interested in just this segment, which starts at point A and ends at point B. Okay? So if we wanted to talk about what the voltage across this wire segment is, we could simply use Ohm's law. All right, the potential difference between points A and B is just equal to I times R. It's equal to the current that's flowing here times the resistance of that segment of wire. Okay, we're just starting with Ohm's law. Okay? What we're going to do in this derivation, just so you know what the roadmap is we're going to come up with substitutions for all of these variables, V, I, and R, and we're going to bring into play the electric field. Okay? So let's go through how that goes. Let's start with the resistance. We showed in the last lecture that the resistance of an object, whatever its geometry is rho times L divided by A. Rho is the resistivity of the material. Okay, so that's just simply a property of whatever metal this wire is made out of. If it's copper, if it's platinum, it's going to have a unique value of rho, just dependent on the material. L is, of course, the length, A is the area, as we just said. Okay, do you guys remember, how can I express the voltage or the potential difference between 2 points in terms of the E field? Yeah, if I integrate E dot dl across the wire, that should give me the potential difference. So if I'm trying to bring the E field in, maybe I should do that. But I jumped the gun. I was going to say this instead. Okay, we'll get there. Remember the definition of current density? Yeah, let's start there. Current density is J, and that's I divided by A. So that's the current running through the segment of wire I divided by the cross-sectional area A. So just simply rearrange that to say I equals J times A. The current is the current density times the area. All right? So this is going to go in for R. This is going to go in for I. And then now let's do what I was saying. Let's talk about the voltage. So VBA, that's going to be the potential difference across the segment of wire. Okay, the potential difference between these 2 points. As we know, that's given by the integral E dot dl with a negative sign out front, integrated between the 2 points A and B. All right? So I'm going to just do this in its full detail. Remember, E dot dl, that's a dot product. And the way dot products work in general is you take the magnitude of each vector, your E vector, your dl vector, and then you multiply by the cosine of the angle between them. So in this case, we're imagining that we're just going straight from point A to point B, and that's the direction the current's flowing in. That's the direction of I, which means it's also the direction of the E field. I showed you that before, right? The E field, if it's creating a current going down the wire this way, is also pointing down the wire this way from point A to point B. So therefore, the angle is 0 if we're going from point A to point B, because we're going just directly with the E field. All right? We're going to assume the E field is uniform inside the wire. In other words, Same E field strength at any point along the wire like this. That's a reasonable assumption. So when we do that, we can pull it out of this integral. Okay, and then what happens, you tell me, when I go from A to B, and I'm just integrating dl. What is the result of that?
B minus that.
I'm just going to get the length of wire segment, right? Because dl is just an infinitesimal piece of the overall length. If I add those all up together, I get the total length from point A to point B, which we're calling L. Okay, so the potential difference is just the E field strength times the length of the wire segment. And then, there may be a negative sign out there. But in Ohm's law, we can drop that negative sign because this is just the magnitude of the potential difference, okay? So we make all of those substitutions now. Okay, in Ohm's law, we have V, the potential difference. That's going to be replaced with E times L, the strength of the E field times the length of the wire segment. That's I times R. I is the current, that's the current density J times the area A. We already said how that works over here. That's the substitution for it right there. And then resistance can be written in these terms, in terms of the resistivity of the material, the length and the cross-sectional area of the material. That's our substitution for R. Okay, this can be simplified a bit, can't it? How so? Drop out the A's, drop out the F's. We actually have a very nice relationship here between current density and the E field. This says that the current density J is just the E field divided by rho. It's the E field divided by the resistivity of the material. So yeah, if you have current in a wire, it's quite easy to figure out what the E field in the wire must be to drive that current in the first place, okay? You just need to know the resistivity of the material. You can also write this in vector form, by the way. Let me just explain how that works. J as a vector equals E as a vector divided by rho. So what this is saying is E is going to be pointing in a certain direction. It's pointing in the same direction that your conventional current is flowing, which is the direction of this J vector, okay? And that makes sense because conventional current consists of positive charge. Positive charge is just going to move in the direction the E field is pointing, okay? Any questions on that? So we'll do some calculations with this now, okay? In particular, we're going to want to know, what the E field in a wire is for a typical sort of circuit. So let's do that. In this problem, we have a 12-volt battery connected to a 12-ohm resistor. The wires connecting the battery to the resistor have a diameter of 1 centimeter and are made out of copper, which has a resistivity 1.68 10 to the minus 8 ohm meters. Question is, what is the magnitude of the electric field inside of the wire in units of newtons per coulomb? So, any ideas about how we could tackle this to solve for E? What would be the first step you would take? Well, we want to get that eventually, right? But I would recommend finding the current I. Right? Find the current going through the wires. Once you have that current, you should be able to find the current density. You should be able to find J, and then once you have the current density, you should be able to find the E field. All right? So try doing that, and we'll go through it in about 5 minutes. pretty minuscule, right?
Yeah.
Well, so newtons per coulomb or volts per meter is SI. All right. Anybody have a result they want to throw out here?
2.10 times 10 to the negative 4.
Yeah, 2.1 10 to the minus 4-ish newtons per coulomb. Let's work it out, and then let's also do the units, which, as you can see, is getting kind of complicated, right? Okay, so first of all, the strategy here is to start by finding the current. We can do that by just using Ohm's law, V equals IR, which gives us a very simple expression for the current. I is equal to V divided by R. In this case, I made the numbers nice and clean. The voltage is 12 volts across the resistor, which has a resistance of 12 ohms. Therefore, we get 1 amp of current, right? The current density, though, J, is that current divided by the cross-sectional area of the wire, okay? Now, the current is just 1 amp. The cross-sectional area of the wire is pi r squared, right? Because it's circular. What is our radius?
1/2
Yeah, so half times 1 centimeter, a centimeter is 10 to the minus 2 meters. So that's the current divided by the area, which is pi r squared. That gives us the current density. What's the current density here?
1.27 times 10 to the 4 amps per meter squared.
Yep. So amps per square meter, 1.273. I'm going to put that extra digit there just for later use. We'll round it to 3 sig figs at the end. Okay. So then the E field, that's just given by rho, the resistivity of the material, times J, the current density. That's if we just want the magnitude of the E field. Of course, it's understood that this E field must be pointing in the direction of our conventional current. Okay? So the resistivity of copper is 1.68 times 10 to the minus 8 ohm meters. And the current density is 1.273, 10 to the 4 amps per square meter. Okay, and just numerically, what does that come out to? What you said before, right? It's 2.14, 10 to the minus 4. Now, what do we expect the units to be if we're talking about an E field? Yeah, we could say it's, newtons per coulomb or volts per meter. You should already know why those are equivalent, right? But let's actually work out the units. So what do we have? We have ohm meters times amps per square meter. So, okay, we have ohm meters times amps per square meter. I'm going to write that as n to the minus 2. All right, so overall, we have ohms times amps times meters to the minus 1. Just cancel one of those factors out, right? Okay, what is an ohm equivalent to? This might be useful. An ohm is a volt per amp, okay? So we're at ohms. I can write that as volts times amps to the minus 1. That's just the replacement for ohms, but then we have amps, and then meters to the minus 1. So amp units cancel. We just have volts times meters to the minus 1, which is volts per meter, which is the same thing as newtons per coulomb. Okay, so that's why the units work out this way. Right? By the way, as the units get more and more complex, and they're going to continue to get more complex because we'll introduce new quantities like magnetic fields, for instance, you can never go wrong if you put all the quantities into your expression in the SI unit. So that'd be meters for distances and amps for currents and so on. You'll get the SI unit out, okay? So SI in, get SI out. Any questions on this one? All right, so we have a little time for some practice. Remember, every lecture has practice problems at the end. When we get through the lecture with some time to spare, we always want to do some of these. This will help you with the upcoming homework. I kind of like this one. It's a long problem with many parts, so let's go through it. Here, we have an extension cord. This is a 2.95 meter long extension cord made of 2 parallel strands of copper wire. And these strands of copper wire have a diameter of 0.4 millimeters. We're going to apply a potential difference of 110 volts between the prongs of the cord. This is typically what you'll find in a wall outlet, by the way. Okay, so we plug the 2 prongs into the wall outlet. Current flows through the wire, through our device, whatever that happens to be, and then back into the wall like this. That's the flow of current in this sort of situation. All right? So let's say the device we're powering here is a motor. And we're going to say the effective resistance of the motor is 7 ohms. Okay? So we can just treat this as some kind of resistance of 7 ohms. The resistivity of copper is given right there. You're going to need to know that. So there are several different questions. First, find the resistance of each wire. So this wire segment here, that carries the current to the device. And it's the same as this resistance for this wire segment. That carries the return current back to the wall. Okay? So get that resistance. Then find the current that's running through these wires. Okay, there's just a single current to solve for. We should be able to do that. Then find the rate of energy consumption for the motor. That's just another way of saying find the power of this motor. And then also the rate of energy loss through the wires. That's just the power for those wires. Okay? Then the last thing you're going to do is find the potential difference across the motor. Okay, so there's a lot of things to do. Let's start by calculating the resistance of the wire and then the current that's flowing through these wires. Let's do those 2 parts first, and then we'll reconvene, then we'll do the next 2 parts. Okay? So remember, for the resistance of the wires, you can use the formula rho times L divided by A. That's going to be useful here. So to deal with that, I have to give you some kind of current as a function of voltage for that specific device. So yeah, it's just, basically get the voltage versus current curves. Yeah, that's what I call it. So I'd have to tell you specifically so it's pretty concerned. But I probably won't put it on that one. We're just going to use Ohm's law for it. So yeah, you have to account for the resistance of everything. You might try drawing like in a sort of a more standard circuit diagram that you're used to. You can just sort of treat it like you have a 110 volt battery connected to a resistor representing the wire on top, another resistor representing the motor, and then another one representing the wire on the bottom. I'll treat it that way. Check your calculation. I think you're plugging in the right numbers. Okay. Okay, let's go through this first part, okay? And I'm going to show you something I sketched out on my paper, which might be useful for you. I've just sort of made an equivalent circuit that looks more familiar based on what we've seen before. So just treat the wall outlet as some kind of voltage source, much like a battery would be, and we'll label that voltage V. Then the wire on the top of our extension cord, that has some resistance, so it's going to be represented by, I'm going to call it lowercase r. Then the device that we're trying to power, I'm going to represent that by uppercase R for this resistance. And we know that's 7 ohms. And then we have another piece of copper wire on the other end of our extension cord, which carries the current back to our source. In this way, we have a circuit and continuous current flowing through it. All right? I represents the amount of current we have. So these are the copper wire segments. Each one has a resistance, which again, I'm just using lowercase r to denote that. Rho times L divided by A. So we are going to take the resistivity of copper, which is 1.68, times 10 to the minus 8 ohm meters. Then we're going to multiply by the length of our wire. That's the length of the extension cord. That's our 29.5 meter length. Then we're going to divide out the area. Again, we're dealing with a wire. Assume it's got a circular cross-sectional area. So it's going to be pi times r squared, where r is half the diameter, so half times 0.4 millimeters, where a millimeter is 10 to the minus 3 meters. So we're squaring that. This is going to give us a resistance measured in ohms. What is that resistance? So yes, this comes out to 3.944. Round that to 3.94 ohms. Okay? Do we agree? Okay. Now I want to find the current. Now basically, to do this, I have to account for the fact that there's resistance not only in our device, but in the wires that are connecting our power source to our device, okay? And in fact, there's a lot of resistance in the wires. We can't really ignore it. It's pretty comparable to the resistance of our device, right? So what I would suggest doing, so here, let me just give you a preview of what we'll do next time. You can literally combine these into a single resistance. You can add the resistances up, but instead I'm going to do it this way. Let's take 2 points on the circuit, which I'm labeling A and B. Okay? The voltage going from A to B doesn't depend on the path we take, so I could just go across the voltage source, and that potential difference would just be V, or I could go across all three resistors, in which case I have I times little r for the first resistor, going against the current is positive, plus I times big R for this one, and then plus another I times little r for that one. So this is the same as saying the voltage of our source is equal to I, pull out that common factor, 2 little r plus big R. Make sense? So the current in question is the voltage of our source divided by 2 little r plus big R, which turns out to be, what do we have, 110 volts. By the way, just a quick note on this. If you plug something into a wall outlet, obviously you're not going to have DC power. It's going to be alternating current. But this is sort of an average of the voltage you get. The real voltage is oscillating up and down, but this is sort of like an average. Okay. So we have 2 times little r, which is 3.944 ohms, plus big R, which is 7 ohms. So how much current are we drawing from the wall here? Yeah, 7.389 amps. So yeah, round that to 7.39 amps. Okay? So you have the current. Now I want you to try the last part, which is find the power consumed by these different parts of the circuit. Find the power consumed by your device, which is over here, and find the power consumed by your connecting wires. It turns out this is kind of a shitty extension cord because it eats up so much of your power, right? It's eating up the majority of your power, in fact, okay? So let's do those. Yeah?
What happens with the direct current instead of the voltage?
I mean, in the problem, we did treat it as if it's a direct current. So we'll learn how to deal with alternating current in
What are the advantages in like when you use one versus the other, like practical, like I'm building the electrical device, how do you
AC versus DC?
Yeah.
Oh. AC is a lot easier to generate on a large scale because pretty much with the exception of solar, every other large scale method of energy generation involves spinning a turbine and then using that to power a generator. And that just naturally gives you AC.
I think even a lot of solar farms do that as well. They have like a cooling tower with mirrors shining up on it.
Yeah, it's a bit different from the other forms, but every other form, like whether it's burning coal or using geothermal energy or hydroelectric,
It doesn't actually generate AC.
you're just doing something, spin the turbine powers the generator, and that just automatically gives you AC.
Okay.
Another thing is transformers, which step the voltage up and down
Okay.
for efficient distribution. Those only really work here. The transformer doesn't really do
For like solar systems, would they be using direct current?
So that tends to just give you
Solar panels.
direct current, so you have to convert that over. But yeah, almost every other form it's just more. It just gives AC as a default. You have to change it to DC if you want. current, so you can plug anything.
This one actually won't have that.
Wait, here's the packet. Here, grab it. Okay. I don't know how the time got away from me. We only have 5 minutes, so let's just go through these. Okay, how do we calculate power? There's different ways we could do it. I'm gonna suggest we do I squared R. Okay? So let's do the motor first. So the power is gonna be the current going through it times R. The current going through it squared times its effective resistance R. So for the motor, here's what we have. We have 7.389 amps squared times 7 ohms. What does that give us?
3.82 times 10 to the 3.
Yeah, so let's say 382 watts. Okay, let's do the wires. Okay, we have 2 of them, so you have to be careful. We have 2 of them, so I'm going to multiply overall by a factor of 2, and then I squared, and then I'm using lowercase r just to denote that resistance. So we have 2 times the same current, which we will square and then multiply by the resistance of each one of the wires, which is 3.944 ohms. What does that work out to?
430.
Yeah, 431 watts. You see what I mean? They're eating up more power just in the wires than the motor's actually using. So it's not a particularly good setup, right? The last question, and then we'll get out of here, is what is the potential difference across the motor? So the point here is the motor is not getting the full 110 volts because you have a potential drop across the wires, okay? So it's getting less than that due to the fact that you lose some potential just going across the wires. Does that make sense? And the way we can find out what that is, how do I calculate V for the motor? Yeah, so here.
Didn't we already solve for it?
We didn't find the potential drop across the motor. We didn't do that yet. That's going to be given by V equals I times R. Okay? So what's our current? That's 7.389 amps. What's our resistance? That's 7 ohms.
51.73.
Yeah, 51.7 volts. Okay, the rest of the potential drop, again, is across the connecting wires. So because you have this resistance in the connecting wires, your device is not getting the full voltage of your source, and a lot of power is being consumed by the wires and not being consumed by your device. That's what's happening here. That's it for today.